Okay. How did the exam go? Is that bad? Really? How long did you spend on it? Oh my gosh.
Yeah, I think I was around.
So was it unreasonably long, or did you suck at it?
No, it's the fact that, well, for me, it was the fact that I overcomplicated the questions. Where looking back on it, I could have made them much simpler. I rely on things compiling.
I see. So the fact that you didn't have a compiler in front of you ended up being a so I guess it's, on one hand, it's good that I didn't put a time limit on it, but on the other hand, it probably screwed with time management. It's like, you know, I missed 4 classes because this exam I coasted through the day. All right, well, I'll be taking a look at them. I don't have them quite graded yet. So a couple of announcements. So on we won't have class Wednesday. I'll be in Illinois. I'm going to try to put up a video for you to watch during class that is me solving the exam. So going through the exam, so I guess I'll find out if it's doable. And I mean, I did the video for the 200 test this morning, and I did it in 12 minutes. So I mean, I maybe don't expect this one to take 12 minutes, but we'll see. If it takes me a full 50 minutes to do it, then it probably was too rough, but we'll see. But I'll put that video up. Hopefully I get it done in time, so you can watch that during class or whatever on Wednesday. Any homework I give you today will be due on Friday, so you'll have a little bit longer to do it. I just have to go into Illinois to a thing for my dad. He's fine, but I won't be here is the thing. And if I was just going to go over the exam anyways, might as well just give it to you so you can watch, and then whatever. All right, makes sense to everybody? You good with that? All right, so let's take a look. We started talking about priority queues, heaps. We already started that discussion, right? All right, we talked about the concept of a full tree. That is a tree where when things are added, they fill in the tree at the current depth rather than letting a tree go too far down in a single direction, which then takes away our ability to build a binary search tree, because a binary search tree is at the mercy of the value currently adding relative to the tree. It's going to go where it's supposed to go, not necessarily go following this heap rule. All right, so we talked about this idea of a heap data structure, which effectively is a priority queue. And not to overcomplicate that, that is, you know, a line. It implements the idea of a line where sometimes important people can cut the line. All right, and this is creating some sort of algorithm for managing that type of thing, and ultimately storing that type of thing. You know, when you think about this, like at a McDonald's or something, you don't necessarily overly complicate the idea of who gets to cut the line. I guess for humans, the answer is nobody, but you don't overly complicate it, but you could imagine like at an operating system level where you have 3,000 processes all running at the same time that you don't even know about. There might be this idea of priority, and it is a more complicated line than we might run into in real life. So this idea of an algorithm to manage the heap is a real thing. All right, so we have 2 flavors of heaps, just to kind of review that. I'll open this guy up. I think we looked at both of these, but we have 2 flavors of heaps. One where the top of the heap is the biggest value, that's a max heap. All right, most important dude is at the top, is at the head of the line. So we're always feeding off. We think of a queue, and this is kind of where heaps become interesting, is it's an implementation of a priority queue. Well, typically we think of queues as linear linked data structures, but in this case, we're implementing it as a nonlinear linked data structure using a tree. Okay, a binary tree. All right. So if we think about, even though this guy is clearly not a line, if we think about it as a line, next guy in line is the person at the top of the heap. All right. That's for a max heap, is the most important is at the top. Min heap, the least important would be at the top. You just decide which of those two makes the most sense. I think we will probably end up looking at Dijkstra's algorithm at some point, where you'll see a lot of similarities to the heap data structure. All right, but we're going to focus initially on this idea of a binary heap, which effectively looks same thing as that example from before. All right, and we have multiple operations on this guy. And if we go in, we look at, so really we have the things we're interested in are probably the insert, the extract, maybe this last one as well. Because the idea is, when we think about a queue, we think about people getting in line and people coming out of the line. All right. So really our important things here are the insert and the extract. All right. So to add an element to a heap, in this case, we're doing this as a binary heap. We perform this algorithm. We add the element to the bottom level of the heap at the leftmost open space. So we visually look at this and we think, okay, we have a tree that looks like this. So let's pretend in this case we are adding X to this tree. All right, so I'm dropping it in on top. So if somebody just walked in McDonald's, they're getting into line. And initially they go to the back of the line. And the current back of the line is the leftmost position at the bottom of the tree. Okay, so my first question is how do we locate the position where we should initially place this value? Notice we're not asking any questions yet of this, is this where he ultimately belongs? We're just saying step one of this dude is put him at the bottom of the tree in the next open slot. Period. No ifs, ands, or buts. That's where he goes initially. All right. So how do we locate the next available spot in our tree? We want to think about this algorithmically. How do I go into this tree and say, where is the next available spot? How do I determine that this right here is the next available spot? How much you pull that off? How do we know that this tree only has 3 levels in it? Because we know the next available spot is going to be in one of 2 places. It's either at somewhere along the line, if you will, of the deepest portion of the tree currently. So in this picture, we know that it's like, okay, you know, we get all the way down to here and we know it doesn't go any deeper, right? So if you go all the way down the left-hand side of this tree and just follow left child, left child, left child, we know we get to this point where we have a level where there is no more left child. So at the very least, we know that, because of the nature of the thing we're dealing with here, that the answer, the next available place is either somewhere along this tree, this level of the tree, or I previously filled up that level and the next place will become this new level. I need to go on to a new level. All right. So let's follow it down here. So let's say I get down to, you know, I'm just going to keep going left tree to kind of get myself into which level are we currently on. So as soon as I hit, so I'm going to say this is level 1, level 2. I can't go anymore. So level 2 is the current depth of this tree with the knowledge that we're dealing with a full tree. Okay. So if I'm at level 2 and this guy's the thing, how do I determine where's the next? So if I'm here, where's the next possible place that I might be? It's this guy right here, right? Because we're going from left to right. All right. So if I'm here and I know I can't go anymore, I need to go up, then over. We have to think about how we're going to implement that. All right, so if I know on the left, I'll go up and then I'm going to check the right. If this is currently taken, as it is, then I know I've checked in this wing, right? So how do I, ultimately, I want to get down to this level. So, and we want to think about this algorithmically. How do I go from here, where I know I've kind of checked this hallway out, if you want to think of it that way. I've gone all the way down to find my depth. No, I'm at the depth that I should be at. Great. Now, how do I go from here to here, and then from here all the way to here? What do you think? How do we traverse a tree based on depth like this? I think I mentioned last time, we definitely need to implement our tree as a kind of along the same lines as a doubling linked list. Nodes need to know about their parent. So we definitely need to be able to walk up the tree. Okay. Well, actually, I guess we could say we don't have to implement it that way. We could always start from the beginning and traverse back down until we get to a left child that is the guy that I'm currently stuck at. And then say, okay, well, now I'm one level up from that. So I'll just dive over to the other side from here. So I could just keep resetting and starting at the top of the tree, but it certainly makes some sense that it might be nice to be able to backtrack. All right, so if we have all these nodes, if I'm here, if I've traversed down the tree to get my depth, and then, we've already kind of written an algorithm before called, max depth, get depth, which tells us the deepest, how far down we go. So in that particular case, we know that the place in the tree, we know what the deepest part of the tree is. So we know how far down we need to go. All right. But we're just kind of doing this by hand. We run down here, we find out, okay, this is the depth where the answer might be, or probably is, unless this far right one is already taken up. Now, we could right off the bat say, if I'm sitting right here, how do I know that the next place that this guy's going to go is not here? Is there a way for me to do a check to say, am I sure that X should not go right here? Under what circumstance would I know that my answer is somewhere along the current level? I found this position by going all the way down the left-hand side, right? So now I've said, this is my depth. One of two things are possible right now. Either I'm creating a new depth, a new layer, or my answer is somewhere along this layer. So if I'm here and I know I'm at depth, depending on how you count, this is 1, 2. Couldn't I then just ask the question of my tree, is the far right available? I followed left child to get down to this point. Couldn't I go right child, and say, is there something here? If there's something here, if there was already an element at 2 levels down on the right child, what does that tell me? That I need a new level, right? So I can ask the question, if I start at the top of my tree and go, whatever my depth was, in this case, it's 2, right child, and that's a thing, then I know that this level of the tree is full. And then I know my final placement is this guy right here. But in this case, I asked that question. I try to go down 2 levels. There is not something here. So I know that I'll be placing this value somewhere along this level, right? And what do I actually, but I don't know that this is the final place. All I know is that there's at least room on this level. There might only be this space, but we see in this case, there's this space right here. All right, so I know there's room. Now, what's the next step? Next step is I'll say, okay, well, I know I'm not going to have to create another level. So now I need to find out where on the current level does this guy go. So I can bounce up and say, is this available? It's not. Then I bounce up, bounce down, bounce over. Is this available? Starting to get the picture here. So now the idea is, how do I ask that question? Because now you're trying to like juggle, like, okay, I bounced up, then down. Well, now I got to bounce up twice and then start traversing down this side. Maybe we start thinking about maybe recursive calls, something like that. Could I say, here's my current depth? If we break this down into smaller pieces, could I say, this is my current depth of the tree down here at level 2? Could I then create a map of all of the potential places that are available? Could I say, you know what, I'm not going to go and search for a final home of this guy. Instead, I'm going to create, maybe it's an array of pointers. And I'm going to get the values at, so this is an address already taken. This is an address already taken. This is an address not taken. So this would be a null value. This is ultimately the dude who has an available spot. Does that make sense? So I can effectively say, I'm going to just run an algorithm and give myself kind of a map of the area. Start at the top, and I would say, I know I need to go down 2 levels. I want to know what this level looks like. So maybe I end up with an array that kind of looks like this. So in this particular case, it might be a, we'll just give ourselves hard-coded information for right now. So we'll say 3, 4, null, null, something like that. That's the only thing I asked for. I'm still not asking where does he go. I'm just saying, hey, give me the current lay of the land at this level for the whole tree. All right, so I know at this level that I have this number of children. Now we might say, well, where does this get kept? Something along those lines. Well, we can deal with that here in a second. This is actually a pretty interesting problem from a how do you solve it perspective, because we can look at this from like a multi-threading perspective and just have kind of a search and destroy, go out and look for stuff. But right now we're going to deal with kind of old school maps of this. So I'm saying, hey, go ahead and paint me a picture of that level. 3, 4, null, null. Is that a pretty accurate picture of what this level looks like right now? Yeah. So then when we look at that, we say, oh, well, so obviously this is my place that guy's going to go. And how did I determine that? Well, I just walked my this array, this linear array, until I got to a place where it said null. Easy enough, right? Okay, so now I know that it's going to be that value there. So now I got to decide, well, how do I get to that? Let me ask you a different question. Could I have, now this guy lives at an address, right? This is a actual node. We don't care that this is a 3, correct? At this point, when we're finding a home for the value that we're trying to add, we don't care about this 3 and the 4. We just care about their existence, not what the values are. All right. So really, we could be asking a question about the level right above this guy. All right. So this guy here has a left child. So we go 1 level short, and I'm just going to 0x123. I'm making up memory addresses. Right, that's left child. 0x221. That's right child. Then we have null, null. And we know that this is the level right above the level we'll actually be adding stuff to. Okay, makes sense? All right, so now when I look at this, well, when I look at this, again, I'm saying, oh, well, where is the, at this point, I'm asking about this guy's left and right child, this guy's left and right child, because I know that I'll be placing my answer one level below. Okay. So I know it's going to go right here. Fine. How do I know? Well, because this was a null value. And how do I know which parent this was? If we go above this, we're looking at, what were the numbers there? That was 5 and 8. So this is 5 and 8. That was the level right above that. And notice that guy's half the length of the guy below, because it's a binary heap, right? So if the level right above has 2, we know that our possible locations will be 4. The next level down, if this level has 4, our possible locations are going to be 8 times 2 times 2 times 2 times 2. Okay, that's how a binary tree would spread out. All right, but again, these guys are memory addresses. We don't care about the 5 and the 8. We care about the memory address associated with this node, the memory address associated with this node. Right. So to get to our level, we really maybe could use 2 arrays, one array of the parents and another array of the children. So if I create my array of the parents, this is to be 0x 541 0x 777, something like that. All right, I'll go ahead and label these. This is the parents. And we know that this is going to be a full array. We know it's going to be filled up with actual pointers, no nulls, right? Because we're dealing with a full tree, and we know our answer is going to be one level down. So that means we have if things are on that level, we have a full complement of parents above. All right. So this array will always be filled up. This is the parents. So in our example here, this is level 1. The fact that I've determined that my answer must be somewhere here on level 2 by first determining that as far down as I can go on the left is level 2. And then I determined that, oh, the dude all the way here to the right doesn't exist. Therefore, my answer will be somewhere on this level. If he did exist all the way over here, then I have the trivial idea of saying, oh, well, I know it's going to be on this level. I think it's going to be on this level. Let's check the far right. Oh, that's already taken. Boom, the answer's down here. Don't need to check anymore. I already had this pointer. But in our case right here, we said, okay, I came down here. This is the level I think it's going to be on. I came down here. This was available. My answer is going to be somewhere on this level. So let's go ahead and map the level. All right, so now I'm going to be asking the question. I want to build these 2 different arrays. An array of the parents, one level up, and an array of the children. We'll call this guy the destination level. That's one level down. Okay, every 2 buckets I go through here corresponds to 1 parent up here. It's a power of 2 thing, right? All right. So as I start walking this, bucket 0, bucket 1, those are already taken. So I keep going. I have now burned that parent. That parent is no longer a viable home. He's got 2 kids, full house, everybody's happy. All right. Now I bump into this. So if I'm thinking about this, I'm probably creating like a loop that's going to loop through all the parents. And for each parent, I'm going to loop through both children. Make some sense? I'll loop through both children. So for this first parent, I'm going to loop through his 2 children. Does that's going to be bucket 0, bucket 1. Both of those are taken. So I loop back up. I move on to the next parent. I need to remember my starting locations. This is 0, 1. So this is 2. I'm at bucket 1 here. So 1 times 2 gives me my starting location for that. 0 times 2 gave me my starting location for this. So if I'm looking at parent 0 here, 0 times 2 is bucket 0. That's where his children start. We check the left, we check the right. When I get here, I'm at bucket 1. 1 times 2 is 2. That's where his children start. 2 and 3. That was the third one. 3 times, let's see, 0, 1, 2 times 2 is 4. So the next child here would be here. So that inner loop always goes through 2 times exactly. Left child, right child. Okay, but the place you're starting inside of this array is always going to be relative to which parent you're currently dealing with up here. And what we have is arrays of pointers, so we can kind of keep track of, well, we have the ability to zip down to the exact place we need to be when we finally find a home. All right, so in our first pass through this outer loop, we say, for parent 0, I'm going to start checking children at bucket 2 times 0, which is 0. Is this guy taken? I checked once. No, yes. Is this guy taken? I checked my second time through. Yes. His children are burned. Spin back up, move to bucket 1. Okay. So now at bucket 1, I'm going to start checking his children. His children start at bucket 1 times 2, which is 2. This is 0. This is 1. This is 2. That's where his child starts. Is this guy available? Yes, it is. So I know I'm going to put him there. And since I'm the first time through that inner loop, right? I'm the first time through that inner loop. That means it's the left child. So I want to say I'm going to go to the current parent, set left child to the value we're trying to add. Make sense how we did that? At least at the high level. All right, so let's start writing some. Well, so let's play this out. So let's say we did add something there. So 0x 222, something like that. So we checked this guy, this first one. This is the first time through that inner loop. If you want to see what the loops look like, so I'm going to say for int I is equal to 0, I is less than, let's say something like parents.length I plus plus. Then our inner loop will be for int j is equal to 0, j is less than 2, j plus plus. So I'm always going to go through exactly 2 times, right? In a binary tree, every parent has exactly 2 children. And I'm going to check those children. I'm going to check them against this guy right here. All right. So inside here, I'm going to ask the question, if children at bucket, you can, if you want to make the math look a little scary in here, you can say something like I times 2 plus j. So the first time through, it would be 0 times 2, which is 0, plus 0. So really, we're saying children at bucket 0. Next time through, it's 0 times 2, which is 0, plus j is now 1. We're checking that guy. The outer loop, we go back now, I is 1. 1 times 2 is 2, plus j is 0 the first time through. We're at bucket 2. 1 times 2 is 2, plus now j is 1. We're at bucket 3. See how that's walking down that secondary array? All right, taking advantage of the fact that it's a binary tree and that we're at the level where we know how many, we know that there is a relation between the parent array and the children array, in that the child array is twice the size of the parent array, even if it's not completely filled. All right. So if children at bucket I times 2 plus j is equal to null, we have a home. We got a place, right? Found the new home. And since we found the new home, where do we put the child? Well, we'll say if j is equal to 0, then what? It'll be parents at bucket I dot set left child to whatever value we're adding. Else, parents at bucket I dot set right child to whatever the value we're adding. We found an opening and we're going to place that person, place the value at the right location relative to the current parent. Make sense how this is working? All right. But if I didn't find a null, then what are we going to do? We're going to spin back through, check this second child, because this inner loop always goes through at most twice. Now, if I'm in this find new child thing here, so I'm not inside this inner if, but I'm inside of this guy right here. I have found a home. After I have placed my value, I'm done, right? He's found his home in the tree. I added him to the correct parent and the correct location, left or right. I'm done. I'm going to just return. Get me out of here. I don't need any more time through this inner loop. I don't need any more time through the outer loop. I'm done. Get me out. Make sense? So we'll put a little comment here. Get me out of the inner, well, get me out of all the loops. I'm done adding the value to the correct place. All right, make some sense how that placement works. Now, this algorithm we just created, when can we do this? We can do this once we know the level that the new value will ultimately be added to. How did we determine that? We went all the way down the left children to determine current max depth. Then we checked all the way down the right children to ensure that level max depth was not already filled. That's when we can then create. So we can say, if it is filled, the trivial answer is the left child of the furthest down left subtree. Else, determine the parents and children arrays from below and perform the algorithm. Make some sense? So then the question is, how did we generate this? Go back to think about what that algorithm is. I've determined, so we're following our steps here where this is pseudocode, right? With some fairly real code down here. Intent is for it to be a challenging assignment, but for you to have enough meat to go off of that you don't get stuck in the, I don't know, a nested loop plus recursion can get a little bit knotty inside of your head, maybe. All right. So our question is how did we generate this? How did we generate this? Both of those things are reliant on us having determined these first two steps. We went all the way down the left child to determine the current max depth. Does this guy have a left child? Yes. Go there. Does this guy have a left child? Yes. Go there. Does this guy have a left child? No. This is where I'm at. Level 2. I counted, right? 0 to 1, 1 to 2. All right, we're good with that? All right. So that in and of itself, remember all hard programs are made up of a bunch of easy parts. Right? So that one step, no big deal. Just following some left shoulder until I don't have one. Then I'm good. This is where I am. So I have a 2 in this case. All right. So now I got to say, okay, I'm at depth 2. Will my value be somewhere on this depth? How do I answer that? I say, we check all the way down the right children to ensure that level max depth was not already filled. So I need to make sure that I can get down here. So I'm going to check the depth of the right child. I can just do the same algorithm I did here, right? So I can say, does this guy have a right child? Yes, I'm at 1. Does this guy have a right child? No, I'm still at 1. Does 2 equal 1? Nope. That guy's going to have a home at level 2. Make sense? If this was filled out, though, I would have said, does this have a right child? Yes. Does this guy have a right child? No. Does 2 equal 2? It does. What does that mean? Trivial placement down here on the next base off of that. Make sense? Those 2 steps. So even though when we visualize it here, it seems a little bit sketch, but the reality of it is not the end of the world for those 2 steps. All right. So now I'm at the point in this example where I said, okay, I got a depth of 2 over here. I have a depth of 1 over here. 2 and 1, not the same value. My answer is going to be at level 2. Now I got to find where in level 2 will this answer reside. All right. And what have we determined? That we need to now create this parents array and create the children array. And notice what I'm storing here is pointers, not values at those addresses. And any place where there isn't a left or a right child, I'm going to store a null, a nothing pointer. Okay. So let's ask ourselves, given that the answer will be on level 2, how did I generate the array called parents? Let's just solve that problem. If I know my answer is going to be somewhere here, level 2, how do I generate a list of all the things, all the pointers on level 1 in this case? What do you think? Well, I definitely need to start at the level right above that, right? My answer is going to be at level 2. I want to collect everything from level 1. So I need to go to level 0 because he knows about all the things at level 1. how many, well, this one's kind of easy, but how many children will be at level 1 if the grandparent is level 0? Level 0 has 1 node. So how many children will be at level 2? 2 of them. If I'm at level 2, where there's, or I'm not, sorry, if I'm at level 1, which is 2 nodes, this is 2 to the 0th power, 2 to the 1st power, 2 to the 2nd power. That's how we determine the size of those arrays. Make some sense? All right. So if I'm at level 1, I know I'm going to have 2 to the 1st power number of elements, which in this case is going to be 2. 2 parents. So I know now how big this array needs to be. But now I need to fill that array. If I know there's going to be 2 things in that array, how many parents am I going to have to check? Half that, right? In this case, if I knew there was going to be 4 children, how many parents am I going to have to check? Half that. There are 2 of them, right? So if I know there's going to be 2 elements inside of my parents array, I'm going to have 1 parent to that guy, all right? And he's going to be at level 0. And that's kind of our trivial case, right? Top of the list, you know, so the first several times, but you can imagine if I go a little bit farther down, let's say the children, let's say the parents were going to be this level. And now all of a sudden I need to think about the complexity of saying, oh, well, in order to get these 4 parents, I need to look at these 2 grandparents. Does that make sense? So now I'm kind of maybe looking at a loop that's sort of kind of like what we just had down below, doing a similar type thing. Okay. So if I'm at this level here and I say, okay, I have, you know, I'm at level 0. I have 1 grandparent at level 0. I need to get the 2 children of that guy who are ultimately the parents of the children where I'm going to place this. I'm going to visit this guy's left child. I'm going to visit this guy's right child and fill an array with this pointer and this pointer. That is the address of that node. All right, that's what we're storing in here. This is the address of a node. This is the address of a node. I want pointers so I can quickly get to those places in memory and not have to ultimately go and retraverse my tree later on once I find his home. You know, because I could do some alternate things with this. I could do like a counting type thing where, you know, this is place 0, this is place 1, this is place 2, this is place 3, this is place 4, this is place 5, this is place 6, and literally count through my tree to find a home. I could do that, right? I could just start counting through there until I find an empty bucket, because I know the order in which these things should have got added. I know this was added first. I know this was added second. I know this was added third. I know this was added fourth. Does that make sense? Interesting thing here. We go back to our search orders, pre-order, post-order, in order. So if I get the question is can I get a thing where it goes 11, 5, 8, 3, 4, then whatever these are? Do any of our traversals that we know about give us that? There's 2 different kinds of searching when you're dealing with trees. One's called a breadth first search, which is kind of what we're looking for here. And the other one's called a depth first search. What we've looked up to at this point is how do you traverse a tree dealing with it depth first. So whether we're doing in order What does in order say? In order says visit the left, then yourself, then the right. Pre-order says visit yourself, then the left, then the right. So if we go this route, so let's say pre-order. Pre-order is going to say 11, and we're visiting the 5, 5, then we're visiting the 3, 3. No left child, no right child. Then we're visiting the 4, no left child, no right child. So that's not the order we want. Post order. Post order is going to say we always visit ourselves last. So post order is going to say, okay, so we get down to here, try to visit left, try to visit right, visit ourselves. That's a 3. 4, 5. Nothing, nothing. 8, then 11. Did that kind of give us our breadth first, but in reverse? We actually did visit the things at the right levels. We just did it. 11 was the last thing we visited. The thing right before that was the 8. It's the 5, so on and so forth. Okay. So we have some ways that we can do some counting down through there. I personally don't think it's as good as dealing with memory addresses, saying, I'm just going to go to my 5th add because that's the next place to add it. Or I'm going to go to my 7th add because that's the next place to add it. I think this is going to give us a more consistent algorithm. So if we're thinking, how do we find these parents? If I'm looking for the collection of things at level 1 here, I have to go to level 0 and ask each of the nodes at level 0 about his children. Collect this memory address, collect this memory address. Make sense? Then I need to go to, well, in that case, I'm done with parents in this particular example. Then how do I get children? Children says, go to each thing in your parents array, because we're no longer traversing the tree now for children. Our children array is going to have how many things? Twice as many as our parents array. And then what am I going to do? I'm going to go through my parents array. I'm going to say, let's record this guy's left and right child and the address of it, including if it's null, which happens to be the default value, right? So can't I just say bucket 0 and bucket 1 of this guy is whatever this guy's left child and whatever this guy's right child is? Whether it's a real value or not, it's the value I want. I want the current address of that pointer, even if it's null. So I'll say this guy's left child and right child are these guys. This guy's left child and right child are these guys. And now I have my child array. Make sense? All right, so for your homework, implement a binary heap. And for, let's see, and let's say that, and the first part of the insert algorithm, your output should be the parent and child array contents. So you're not actually going to place the value, you're just going to produce this array and this array in preparation for placing those values. Make sense? All right, so just those 2 arrays. And that'll be due on Friday, since we won't have class on Wednesday, but I will have a video up that, I mean, you can watch it or not watch it. I don't care what you do, but the idea is I'm going to go over the exam in the video so I don't have to spend class time going over the exam. But if you do have questions about something from the exam, I'll take those on Friday before we get started. Sound good? Questions, comments, concerns, bribes? All right, I will see everybody on Friday. And I will be available on Slack and stuff if you have questions when you're working on the homework. I'm not going to be out of communication or anything. I just won't be here or in a place where it would be reasonable for me to do a Zoom class.